Okay, hello everybody. Good afternoon. I'm happy to see you all here joined today, and it's already 4 p.m., so it's time to get started. But I would like to wait for another minute to give a chance to others to join as well. And in the meantime, I would like to ask you if you can see me well and hear me well. Also, if you can see my screen, I would appreciate your comments in the chat. Okay. All good. We can see and hear you well. Top. Thanks for confirmation. And we're gonna start in about 1 minute. Okay, it's 2+4, so let's get started. The other ones who will join us later, they will keep up with us. So let's don't waste time. So hello and welcome everybody to this today's webinar. For those who don't know, my name is Roman. I'm head of engineering at SDC Verifier. I'm going to host this webinar, and the topic of today's discussion is EN 13001 compliance, and also the extending port equipment lifetime with SDC SAM. So be aware that this session will be recorded. It will be later uploaded also to our YouTube channel. So if you want to rewatch it later or share it with your colleagues, please do so. Not hesitate. And I'm always a fan to making our discussion a little bit more interactive. So if you have any questions during my presentation, please do ask them. You can either unmute yourself, ask them directly, or we will have anyway a Q&A session in the end of this webinar. So I'll try to answer them all anyway. So yeah, for now I will turn my video off just to make it a little bit smoother and make sure you have no interruptions, and let's get started. So, I'll swap like this. Let's start with the agenda itself. So I'll start from a very short introduction who we are. For those who don't know, we will stop in detail on the challenges in port equipment verification, focusing on the key pain points in complying with the EN 13001. I also mention a practical checklist on how to make sure that you need this verification or you do not need that. I will highlight solutions with SDC Verifier software, so how to build the effective workflow and verify structures according to standard. And what's more important, how to extend the structure lifetime with SDC SAM. So introducing the tool, also highlighting the key features and the principles of the lifetime extension, and a short summary in the end. So who we are, as you probably know, we are a software development company, and we developed already a few products. So we started from a extension software to popular FEA packages like ANSYS, FEMAP, and SimCenter 3D. But also then we later noticed that, okay, there are advantages and disadvantages of each of this package, of course, because this is a unique program, and we came up with our all-in-one software solution, which is a completely standalone tool covering basically and gathering all the covering basically all the gaps we noticed in our work. And also we have a third product which we call SDC SAM. So this is a brand new tool. I will not say much now, because anyway I'm going to explain it later. We have currently 3 offices in 3 countries. We have many companies already using our software, a lot of happy users. But besides that, we also the company who provides engineering consultancy service, and that's actually where it started from. Because we originally started providing services and noticed a lot of routine that could have been automated, and that was the reason for us to develop our own tool that allows us to focus more on real engineering problems, on solving them rather than on the repetitive tasks and routine that can be, of course, automated. So we provide a wide range of services, starting from design checks and optimization, structural calculation. We also support clients at certification, tenders. We build digital twins of physical models, conducting measurements, inspections, and etc. But what's more important, today's topic is not something new, because this is our field, and this is definitely not a black box for us, because we have a long experience behind. Some of our clients you can see related to the heavy lifting industries on the screen. So again, this is not something new for us, but this is something that we have been working with for a long time. Although we're talking about the heavy lifting equipment today, we're of course involved in more industries, as well as our software, which has been used in many of them, starting from oil and gas industry or civil engineering, offshore, machinery equipment, and so on. And we have also a lot of users around the world in many countries. Some of them you can see on this screen. But coming back to the main topic of the webinar, which is EN 13001, with no doubts, I know that you know what this standard is about as you joined this webinar. And you probably also know that before the introduction of EN 13001, the industry relied on various national standards and guidelines, such as, for example, DIN 15018 or old NAN standard, and of course, FEM 1001 standard. And one of the problems with these old rules was that they were created back in early 80s or even earlier, and haven't kept up with the newer engineering knowledge or modern design tools. So you also know that many crane structures that are still in use today were designed decades ago in accordance with FEM standards you can see on the screen, which of course define an expected service life. However, these designs were typically based on manual calculations, often resulting in simplified models or conservative assumptions. And consequently, the actual condition of such cranes has become increasingly uncertain, so both in terms of local problems and global structure integrity. So to address this limitation and to improve the accuracy and consistency of structural assessment, there was a need in revision and harmonization of standards, and that's basically where development of EN 13001 occurred, and aiming to streamline future application by introducing more harmonized principles. Let's say modern design philosophy, as also FEM briefly mentions, including methods with limit state principles. So here you can see directly EN 13001 itself, and well, frankly, when compared to all the standards or other national rules, it becomes obvious that this standard offers more structured and reliable way to evaluate crane strain and also fatigue. However, with even this progress, a major challenge remains. And what I mean here is figuring out how much longer existing structure can safely be used. So one of the biggest challenges, of course, the lifetime of port equipment. And that's the first challenge I would like to point out right now, because this is a very common story that people around they have in the old structure, for example, like this one on the screen. And yeah, they were manufactured in the 60s or 70s or maybe later. But the question that still takes place is, what is the current state of the structure? And what's more important, yeah, we all see that it approaches the end of lifetime, but this structure is still in operation. So the questions we keep asking ourselves is, what is the actual remaining lifetime of this structure? Yeah, because that becomes obvious that replacement and embellishment of this complete structure is a huge investment, and nobody wants to do that. I mean, if there is any chance to modify that locally or to come up with the reasonable repair solution, we all would like to extend this lifetime. And the main question which we still have on our agenda is, okay, can I use it for another 20 years or 10 years or whatever this number is? Of course, these questions, they are often followed by the structural damage or cracks. Some of them you can see on the screen, for example, like the crack at the pin connection or this bracket, which is obviously a fatigue-prone zone, or maybe some deflected parts, so that's more a buckling issue. But yeah, but fatigue or a local structural damage, this is something really, really common for all these designs. But even if you do not have that, there is another question. Okay, I do not have any cracks, but I have severe corrosion in my design. So I did not see visual damage or cracks, but let's say the thickness reduction of my main steel structure has reached up to 40 or 50%. So is this still safe enough? And yeah, and in many cases, when we get a crack, we make not very deeply thought steps like, okay, what do I need to do next? So probably it takes a while to make this decision, but this time results in even more severe problem, like in this case, where you see the original crack was over 30 centimeters, and it has become over half a meter. So that was rapidly growing, and then we need to make decision basically. So often these decisions are followed by with no calculations. So like in this case, okay, we decided, client decided to weld the cracks, to drill the holes at the ends, which sounds as a pretty reliable solution, standard solution, by welding also extra welded plates to reinforce and to increase the stiffness at the corner, which was obviously the weakest zone. But the drawback is that this often results in the crack reappearance, like in this case. So if I zoom in, you can also see, okay, we drilled that hole here, but in some time, basically this crack came through and that was continuously growing, and the new crack appeared at the newly welded reinforcement. So doing something or welding something because it looks reliable at first glance, or it looks big or strong, without any calculations, can be extremely dangerously misleading and leading to another issues popping up, which also solving of which is quite a challenging thing. We could say, okay, many of crane owners or the companies, they do some preliminary calculations, let's say hand calculations or following some spreadsheets. But the biggest drawback of this is that when we do have such complex problems, we have also limited accuracy, and basically these calculations, they are prone to human errors and inefficiency. So at the development of the and also the of the FEM standard and the EN 13001, we had also development of the FEA methods, so something we call simulation. You see in this screen an example for the floating crane, which has some laughing motions, also slewing motions, and that is something that provides us with much more accuracy for our structures. Yeah, because it directly simulates the real behavior of the structure, and it pays off, of course, in the end, because the results accuracy is high. Yeah, one of the pictures I do like. So basically, this is the FEA results on top of the real structure. So the biggest advantage is that you can directly follow the stress flow over your structural members. You can see which zones are more stress concentrated, which are less. And that is not a black box anymore, like with hand calculations, which still take place. And yeah, this is of course will be integral part of our engineering life in the future. However, for complex problems and issues like that, we need to use advanced techniques, like in this case, the FEA. The next challenge I would like to highlight is that many heavy lifting companies and port operators, they still do not use this FEA. Yeah, so on the one hand side, we have advanced techniques, we have these solutions, but they do not use them for some reason. And yeah, I could make another webinar on this topic, talking for a long time. By the way, in the previous webinar, I was partly covering this topic, but we also decided to develop a very short checklist to give you an idea whether your structure requires structural verification or not. So be aware that after this webinar, you will be you will receive basically this brief checklist. So if you're hesitating and you don't know whether you need the structural verification, or you want to answer some basic questions, or some of these questions taking part of your case, yeah, I hope that will be helpful for you to make the right decision. So let's talk about the typical fatigue analysis workflow according to EN 13001. Yeah, because obviously if we want to extend its lifetime, we need to know what is the current state, and we need to calculate this so-called cycles to failure or fatigue damage. So what you typically do having such a complex scenario, so you're building a digital twin of your physical model. Yeah, so basically you're translating your physical model into the numerical solution, and you are trying to come up with the reliable calculation scheme and the loading scenarios. So this standard prescribes these things. I will mention that later. The next thing after that, after you define your loading scenarios and load cases you have to consider, you need to clearly define what is this working cycle? What is that in your case? What are the working conditions of your structure? What are the relative number of cycles? What is the total number of cycles? So these are the crucial parameters for assessing your remaining lifetime. Another thing which is also crucial in this case is something we call the load spectrum. So you need to know what is the equivalent hoisting load, or what is the equivalent lifting capacity over its historical usage. After it's all done, basically what you do, you calculate so-called delta stresses for all the scenarios we defined earlier. You need to clearly define the notch classes and the weld quality. So depending on the whether you have a full pen weld or a single fillet weld, or what type of connection you have, poor quality, good quality, that results in all these kind of values. Next thing we do is a calculation of stress history parameter. So that is the new adoption of EN 13001 when comparing to FEM standard that is relied on the kappa factors, for example. And after it's done, we can, of course, determine the limit design stress range, which you compare with your delta stresses. Yeah, so this is the last step, of course, to define what you're looking for, which is the fatigue damage or cycles to failure, or answering the question, what is the remaining lifetime? But let's briefly talk about each of these steps, just to give a little bit more clarity on why it's important and why it's still the challenge. So when talking about the digital twin of the physical model, that is obvious that, okay, if we, like in this example with the crane, okay, if we have a trolley and hoisted load, we load it somehow, and we know that the forces and loads are transferred between the structural members, so from boom to legs and so on, through the joints, through the connections. So connections are transferring forces between various members. And typically these connections, they are more loaded, and these are the potential stress concentration zones. So we need to make sure that all important connections are accounted for in detail. Simple example, even if you use FEA approach, and you followed with the BIM modeling approach, so that's the really simple one, and this is a very common approach for really many companies across the industry. So what you see in this picture, okay, I have some critical areas with high values of utilization factor. And yeah, if we look at this waterside crossbeam, I see that big parts of this crossbeam, they are highlighted in red. Yeah, just for those who don't understand how to read it. So orange is and red is not okay. Everything that is below is okay. This is allowable. So on the one hand side, we have a big area. Yeah, that's a large component. So over the 2 meters height. So we have some problems there. However, if you go to the plate modeling approach, so more detailed one, and you conduct the same, it becomes obvious that the cross section of this girder is not critical, as we see that for the beam model results, which are based on one direction of the finite element. What we can see from this picture, okay, we do have some locally higher stress peaks, but these are rather local than the global problem for the full component. And very often, this issue is somewhere inside the structure. For example, like here around the hole made, here at the transition from crossbeam to the girder, or at the corners. So this is more a local issue than the global one for the member. Yeah. Another example, having again the same container crane. So if we look at the pylon head connection, so in this case, we see that we have some stress concentration points and fatigue prone areas, but answer the question, is that possible to account it for with the hand calculations? Yeah, will you get the same level of accuracy? Well, of course not. So having this advanced technique and basically sticking to more detailed modeling approach is a key component here. And especially if it's concerned to critical members like hinge, or for example, like backstay and the forestay. Yeah, because these are the components which which take most of the load. So this is definitely not something we want to fail. Yeah, so we have many things like that in different kinds of port equipment. For example, like in this hopper, where we have a lot of stress concentrations, or even the cylinder, where we have here at the thread, we have relatively high fatigue damage, or even if it's just a simple boom and we want to assess the remaining safety margin or the sheaves, whatever it is, we have many stress concentrations which are everywhere, and this is essential to stick to this method. One more example I would like to highlight, I took it on purpose. That's a simple tube. I think you've seen this kind of connections a lot, also in cranes. So that's a butt weld connection for the tubular joints, where you have the different thickness transitions, from thin to thick. So at first glance, it sounds, okay, this is pretty simple. However, are you able to account for correctly the stress distribution with the beam model or the plate model? So sometimes you really need to dive into even more details and follow volume modeling approach, like in this case. Just an example. So here you see from the outside, it looks like, okay, this is pretty fine. However, when you look at the inside of this connection, you see a very high stress concentration right at the transition with your plate thicknesses. And this is caused by the eccentricity of these two plates, which is really, really challenging to account for with hand calculations and even the plate model. Same is concerned to any kind of connections, which are bolts, which we of course highly recommend to model in detail as well if you want to determine the actual capacity. Also per bolt, not just following a let's say simplified approach. So I have number of bolts, I have the total force, and then I do the calculation. But you have 200 bolts, and it can be that only one is not okay out of 200. And basically, by replacing or adjusting this bolt, you're fine. So these examples, they are applicable to all kinds of structures. Some of them you can see in our project examples. So it can be whatever. So it can be RMG cranes, all kinds of loaders and unloaders, jeep cranes, container cranes, more STS cranes with different configurations, or overhead cranes, ship unloaders, floating cranes, again, ship unloaders, stacker reclaimer, straddle carrier. So all kind of equipment. It's basically everywhere, and this thing is essential when we want to comply with the Enter 2001 rules. So another thing is we were talking about is the calculation scheme or loading scenarios. So if we look at this crane, okay, we have many loads. We have hoisting load, we have a trolley weight, which is running back and forth. We have crane movements here and here. We have some buffer conditions. And there are actually a lot of different load situations, and all of them, they are summarized in the simple table of EN 13001. So it's divided by the category. So it's regular, occasional, or exceptional loads. But it includes, again, it includes so many different variables, starting from load categories, positions of your trolley, yeah, because it can be here, it can be there, anywhere, basically. Load direction, whether it's traveling to the water side or to the land side. Different dynamic factors, depending on which case are you checking. Different partial safety factors, which are all different for regular, occasional, and exceptional cases. So basically, all the situation is resulting into the hundreds and thousands of load cases to be considered. Again, depending on your structure, but very often this is a considerable number of load scenarios. Another key pain point in EN 13001 compliance is determining your working cycle, like I said. So in the older standards, for example, or more conservative assumptions, you assume that, okay, when you do design of your crane, you assume that, okay, I'm lifting up the load, then my trolley goes from one extreme position to another extreme position, and that happens like 2 million times. But is that really true? Not really. But basically, this is something we call cycle. So this is when you go from maximum to minimum and then back to the maximum. So that is basically one cycle. And applying such a conservative assumption to your especially existing structures is definitely not reasonable, because very often this is a non-even distribution. For example, like in this case, where we see that, okay, I have definitely less movements at the tip of my crane or also on the back reach. Yeah, and depending on the size of my vessel or the ship, depending on the storage area, so whether I have some, where do I have the lashing platform, or for example, the lanes or trucks, I have a different frequency of the movements. And in this case, it occurs, in this example, it occurs between the legs and slightly going beyond the hinged connection. So what it means in practice, it means that the accumulated fatigue damage will be, of course, much less overall for the crane when you have the trolley traveling from one extreme position to another extreme position. This thing you have to determine accurately. Next thing I mentioned briefly is the load spectrum. So let's say you have a loading capacity of 60 tons, and the question is that always the case that your crane is lifting 60 tons? I mean, throughout its lifetime? Of course, no. And for this purpose, we have different design load spectra. For example, like in this case from older NEN standard, it just nicely explains, So if that's the case, then basically you need to follow with your load spectrum factor of 1, because the crane is frequently loaded with the working load. But reality is such is that we have different container sizes, we have different content, we have different occurrence, and that results in the, well, in practice, this results in the lower equivalent hoisting load. So determining the load spectrum factor is a key parameter here as well, and EN 13001, of course, defines this this characteristic as well. What you do next, I mentioned that you need to calculate all your delta stresses, because on the one hand side, we have different trolley positions. So we have movements from here up to here, then we have from here up to here, and so on and so on. And each of these let's say, traveling range results in different maximum and minimum stresses. So EN 13001 clearly tells you how to calculate this delta stress. And basically, if you look at the graph of this stress cycle, this is exactly this. So you load with the maximum, you load the structure with the maximum load and then with the minimum, and you need to define it for every single spot in your crane, depending on moments. Yeah, and these categories which we want to consider for realistic traveling conditions and positions of your trolley. The next step is the notch classes and the welded quality. So what you can see in this picture is, just a simple example of what is the good quality and what is not so good quality. But EN 13001 is a very specific standard, and it defines those things depending on what kind of connection you have defined. So if it's a butt connection, if it's two plates welded together, T-section or butt section, depending on the load direction. So if it's along the weld direction or perpendicular to the weld direction, depending on the whether you have a full pen weld or single fillet weld, and of course, what is the weld quality we discussed here. So this results in certain numbers, and these numbers are different for different kinds of connections, welding qualities, weld types, and so on. So this is a crucial step. What is left there is something that I really, and I think most of engineers, they are really struggling with. This is something about the stress history parameter. Because you need to summarize now all your delta stresses and the relative number of cycles to calculate the stress history parameter, define it with the limit design stress range, and of course, furthermore transferred to fatigue damage or cycles to failure. So why it's struggling point for everybody? Because if you follow a simple principles or hand calculation approach, that becomes definitely a time-consuming calculations. Even with the software solutions, this is still a time-consuming calculations, because on the one hand side, you have a complex FEA package. You want to capture all those stress concentrations, all those different and complex behavior. But on the other hand side, you have all those complicated formulas you have to follow. And that is exactly the purpose we developed our software, which suggests the optimized solution, how to deal with all this. So basically, it takes the model, apply automatically the load combinations for a lot of these scenarios. We can quickly recognize all the welds, welded components, or other members, conduct checks according to EN 13001 or other standards, quickly generate report, make sure it's fine. If it's not okay, we can also optimize it. But what's more important, the workflow is saved. This is why you have these two arrows for. Why do you need it? Especially when working on some solutions, you are testing different, plate thicknesses, you are testing different loading scenarios, and that results in running in circle, and you definitely don't want to repeat it all over again. So, or for example, you want to go with the higher load capacity. You have the load capacity of 60 tons, but you would like to increase the efficiency, and you are wondering if 70 tons is still allowable in your case. So basically the saved and automatic workflow, this is definitely a huge game changer here, because all those steps are then taken over by the software. So what happens, basically the software allows you to create the model from scratch. So you can account for any single component you need, or you can create a parametric model of the crane just by filling in all the dimensions you need. You might say, okay, but I have already some model in ANSYS or FEMAP or Abacus or some AutoCAD file. You can, of course, import that. That's still compatible with any software you see in the screen. What's also good is that all those complex load scenarios, I know that many engineers, they got used to use the Excel files with this kind of matrix functionality, filling in with factors according to standard. So good news is that, you can just copy that and paste it from clipboard, so you save your logic if you really want to proceed with it. But for those who don't want to follow that anymore, we have developed a predefined load cases. So basically, your loads applied to the model, they're categorized according to EN 13001. And if you preview it, you can see directly, okay, what is my dynamic factor? What is my pressure safety factor? You can play with your magnitude of the load. And you see also the model factor. So that gives you a clear overview. It also saves time on opening the standard, because you don't need it anymore. I mean, in terms of finding this complex table. So you just click a button, you get the table you need. You click the dynamic factor, so you can adjust them manually if you like. And yeah, that saves time and makes it more handy. Same, of course, is followed with other standards, for example, like Eurocode in this case. And yeah, you get it. You get a clear overview in the software. But then there is a question. Okay, we have these hundreds and thousands of different load cases for our crane. Which one is that really important? I mean, do I need to calculate all of them, especially when I do some reinforcements? So like in this case, we had 132 different load cases, but it turned out that only 8 are really important. For example, load set 70 causes the highest stress values at the green regions, yeah, and not the others. Load set 33 is important for yellow regions, and so on and so on. So for example, if I do reinforcement specifically here, where I see that the yellow color takes place, so I know that the highest stress value is coming specifically from load set 33. Do I need to use then the green one? So for load set 23, no, I don't. Same thing is related, for example, to jeep crane. Yeah, so you see that, okay, this yellow short braces and here the platform, the highest stress level is coming from extreme position number 5. While for the front arm, position 2 is the most important, not even 1 or 5. So this is an intermediate position. So this is very useful to know. But then there is a question. Okay, I have one load set, but one load set consists of many loads. Yeah, so on load, on weight, hoist load, wind, and so on. Which one is that important? We went further and we developed a breakdown of these things. For example, if I have a zone overstressed and it's coming from load set number 5 or 14, I see that, okay, I have the list of loads included in this load combination because that happens simultaneously. And I know that 38% of the platform load is important for this area. 28% of the stress is coming from the conveyor load, and only 10% is coming from the wind load. So it directly gives you idea that, okay, the platform dead load is not important, neither the equipment dead load, while the own weight of the structure is only 10%. So especially when improving your structure or when assessing its realistic outputs, basically you can also dive deeper and see whether you made any conservative assumptions at the initial stage or not. All this is backed by the Nastran solver. So this is a SimCenter Nastran at the developed many years ago, basically in the 60s. By NASA, so NASA Structural Analysis. And yeah, after you do this analysis, what you can do, you can quickly recognize your structural members, whatever it is, whether it's a joint, beam, weld, or buckling, or plate fields. Yeah, but when talking about the remaining lifetime, of course, the welds are the most important ones. So good news is that with one click, all welds are defined automatically. All the stresses converted into the weld direction. All weld intersections are also defined, which are typically the weakest points. So yeah, in 99% cases, you don't have to take care about it. Going further and talking about the weld classification, I was talking about 5 minutes ago. So we have a nice quality and the bad quality, and we have all those kind of different numbers. So good news is that it is also automatically defined for your structure. You don't have to manually set it up. Yeah, and if you look at this picture, you can see all those different colors with different numbers. These are exactly the notch classes that are appropriately used in the formulas. So if you have a butt weld, then it's defined for the butt weld or T-joint or whatever it is. So this is no more a routine job. This is, of course, applicable to any kind of structure, not just this port crane, but also overhead cranes and the others. The next thing is the real crane usage. Good news is that, okay, we were talking about all those relative number of cycles and complicated movements. advantage is that this can all be translated into the software solution. So basically, each and every movement with relative number of cycles can be defined in the software. Same thing is related to other kind of structure, for example, like this RSC crane or overhead cranes. So whatever it is, this is a software solution in the end. Even if you did a hotspot fire analysis determining those things, or for example, like the real measurements which took place for trolley position spectrum for this unloader, basically this is all translated into the software. Or the jeep cranes, where you want to consider different positions, different angles, or the ship loader, like in this case, which has the retractable boom, and you have different positions of the retraction or the angles over the height. So yeah, this thing is definitely part of the software procedure. After that, you of course logically do the fatigue analysis itself. So basically, in this case, we're talking about the N13001, but of course there are many more standards available, including the Eurocode FEM standard, which we mentioned, or the same DIN standard. Results accuracy, this is something that we're proud about, because this is very accurate. Some of the examples you can see on this screen, and basically this is something that you are looking for when talking about the validation of your numerical model and the physical model. Yeah, very briefly, because sometimes you need to optimize your design. So you found a crack or some damage and you need to play with it. So this software does it as well. Like, for example, in case of this floating crane, where there was a significant crack found in the top node of this upper arm, and the node was updated, successfully implemented into the structure, and that's how the problem was solved. Or can be anything, basically, even the buckling of some member, which can be automatically optimized by the software, or capacity above the weld. So if you want to make decision, do you need to go with the full band weld or partial penetration, whatever. We have so many information I just mentioned, and yeah, this is something that you're not going to lost with, because it can be all reported with our automatic report generation. So you can export this to the Word or PowerPoint or PDF documents, any kind of information. So whether it's FEA model related things, yeah, so I mean setup, or the outcomes themselves, or some extensive overview. But let's come back, let's make a step back to our typical fatigue analysis workflow, because we concluded that, okay, we need to come through all these steps, which is fine because we have a software solution for this. But I think something we did not mention, and something that is not clearly defined in the N13001, especially in terms of existing structures, what do I need to do next? Because you determined your fatigue damage, you have cycles to failure, but important thing is missing here, which is inspection, of course. Yeah, you need to validate your numerical results with the physical model, because this is also for safety reasons, because it can be that okay, you have no problems in your FEA model, but in reality you found a crack. So why did that happen? So maybe you did some optimistic assumptions while doing all this verification, or maybe you missed something, or something concerned to each of these steps, so to load spectrum or working cycle, whatever, or vice versa. Maybe you found a significantly high fatigue damage, but inspection results show nothing. So on the one hand side, we have fatigue damage or cycles to failure. On the other hand side, you have inspection results. But then there is a logical question. What do I do next? Yeah, after your model validation. And that is actually something I would like to outline as a separate challenge in this lifting equipment design verification, which is reliable maintenance and inspection schedule. Yeah, because this is often the case and common question when we're asking ourselves, okay, when and what was inspected? You have so many FEA results. you have some inspection results. How do you manage all this? What is the health status of your asset? Yeah, so okay, you found some results, you have some conclusion, you did an inspection. What is the health status of it? What was found? Yeah, what are the details? I mean, you have like hundreds of pages of report, but how do you manage to organize all this? When do you need to check it next time? Let's say you made an inspection, you found nothing, but when do you need to check it next time? Or vice versa, you found a crack, but what is the period of inspection you have to follow? Is the crack still acceptable in terms of overall structural health? Yeah, you found a crack, but let's be honest, crack at the small bracket, let's say between, I don't know, the leg and the sill beam, and crack in the forestay or in the hinge point are two different kinds of cracks with two different levels of responsibility. So is this crack is a local problem, or does that make an influence on your overall structural health? Yeah, and the most important, where do I store all this? You have so many things. How do you organize them and how do you manage them? So this is the primarily reason for us to develop our brand new tool, which we call the SDC SAM. This is Structural Asset Management Tool. So I'll spend a couple of minutes to make an overview. What is that? Because we truly hope that this tool will be, we're convinced it is already a game changer, because frankly, I keep saying that, but the more I talk to people on this topic and asking these questions, the more I'm making sure that there is either no maintenance control as such, or it's really in at poor level. So we truly hope that this tool will be useful for our engineering community and close these questions. So what you do, first of all, you need to log in, because that's a web-based tool. And you have, depending on your role, depending who you are, you can have different permissions and you can have different access to the information within the tool. Yeah, so whether you are a third-party inspector, for example, or crane operator or engineer or whoever, you can have different access. So what you do there, you go here and you see the list of assets. So it can be basically anything. What we call asset for us is the global structure. So it can be either ship unloader or gantry crane or STS crane. It can be anything. This is your asset. What you can see here is that, okay, you have a description, you have its name, you have different department addresses and so on. You can see them on the map, yeah, depending on their location. So let's say you have 100 cranes, that's very useful. If you don't have any asset there, you can add it manually here, or you can make some custom asset, of course. And what is cool, you go to details of each asset and you get a overall information about it. You know, okay, where is location? You have general health status here per component. So you see in general it's good, but you have still some parts in not good condition. You have pictures of your FEA model. You have the drawing to quickly get access to. You have the real picture. So basically you get this information per each asset wherever you go, which is very useful. You have the information, when was it last inspected, how many days left to next inspection. You have all this storage of FEA results. So it's not just a paper-made report, but this is directly dynamically accessible plots. So you see summary, executive summary, okay, these spots are not okay or okay. You have days to inspection, okay, last day, last action date, and so on. But also you have a breakdown to your component dates. So when you go to the administration, you can see that, okay, I have different departments, I have engineers, terminals, and so on. So you can add department, whether it's internal or external. You have users with different roles, like I said, with different permissions, who can access different kind of information. So you can really tailor this according to your company rules. You can set up asset types. So it's typically STS crane or gantry crane or whatever, but it can be anything. So you can add your own asset type. You can determine also inspection property definition. So whether you're focusing on a paint damage or localized corrosion or deformations or fatigue. Yeah, so there are, of course, default parameters, but you can add your own if you see that something is missing. So this is very useful for those who are conducting this inspection. Yeah, so if you want to be really detailed, basically this is a full checklist available during your inspection, and you're not doing that after you finish inspection, but you're doing this during your inspection, which is very useful. So you click on an item or asset, you make a note, okay, there is a corrosion file, you take a picture, it's uploaded, it's right there. So yeah, like I said, here we have mostly general information. So you know where it's located, you see general health status, you see days to the next inspection so you don't miss it. But of course, the general health status is defined by the summation of health statuses of your components. What do I mean by the components? Components are practically your structural components. Yeah, so like in this case, if it's a bridge, backstay, pylon head, etc. So for example, if you focus on this component, which is the waterside sill beam outlined over here, you have information for this component. So again, you have maximum utilization factor found, you have health status per component, last day inspected, days to next inspection, and so on. And if you go to this one, then it's further divided into parts. Yeah, because structural component is a pretty large element, and yeah, it contains many other parts. For example, like part 1. In this case, it's 14 parts, but part 1, which in our case has poor condition with the maximum utilization factor of 1.16. We see that, and we want to find out the details. Yeah, so although you have all those results available for a component, you click on the details and you go into the part itself. So you see, okay, in this area, I have locally higher stress peak at the corner. So I have my panels, stiffeners, welds defined, and I have in total 4 tickets. So I have 4 points to check in this specific part. When I go further, it's divided by so here you can see the breakdown. So you have component, part, and then it's divided into panels. Each panel is divided into plate, stiffener, and weld. And you have kind of a breakdown overview. Where do you need to look at and what is not okay? You have a list of tickets. So of course, per structure part, and then further with this breakdown. So you know what do you need to check. Yeah. What do I mean with this ticket? Ticket is the action required from the in terms of inspection side. So you have this list of tickets, and you can so this is basically, in fact, the list of all critical points, which can be organized in jobs. So I have ticket for one part. I see that it's completed. I have a date when it's completed. I see something is overdue. And I can assign it directly to users, to the inspectors or to engineers. And this way you're able to plan your work. You assign it to people, you define the timeline and organize a job itself. And when somebody goes on site, basically, you can change the ticket status from pending to completed. And you know that, okay, then it's filled with the, so from pending to completed, and you know that it's filled with the all necessary information, characterizing what was found, how was it found, etc. You can also add ticket information like, okay, I found paint damage, I found corrosion, localized corrosion, some initial fatigue, and so on. And if this one is limited and the inspector requires to have a little bit more extensive data, this is of course possible with the advanced description. Yeah, but idea is that there is a very advanced way to describe the problem to make the story clear. After that, you also have a tab to all resources, so all kinds of reports, FEA models, drawings, links, or even some links to the PLM system. They're also available, so you can upload it here to this database, and this information can be added to assets, to components, to parts, so you can sort it in a way you like. And what's also cool is that access to files and functions depends on the role of the user. So just a quick overview how it works. So like I said, okay, you have You have very brief overview, so you can add those assets. You see them on a map. You go to details. Okay, I have this general status. I go to components. Yeah, I have, so first of all, this general results here, just for a quick review, where do I have problems? But then the complete breakdown is, of course, followed by the components. So on the left-hand side, you see you have this component parts. You can sort them by numbers, by statuses. You can go to panels, welds, etc. And yeah, once you click on the part, you go into the sub-asset. So you see, okay, this is the crossbeam. I have results for the crossbeam. I have the health status. Yeah, I can go even further to part of this crossbeam. I see that, okay, there is a detailed results I see. There is a plate, there is a weld. So I know exactly where do I need to look at, for example, like this plate with stiffeners. Yeah, so I have certain number of welds. I know which weld corresponds to what. I know which one is in poor condition, which one is in good condition. I know results per this weld. So I don't have to open report at all. I can characterize this weld and support it by the inspection results. So, okay, according to FAA is this, but after inspection is done, it becomes this, and that basically determines your asset. And if you don't know where it is, you see, you can zoom out and see which component it corresponds to, and so on. This can be done to any kind of structure, any asset. For example, like in this case, this is for also type of crane. So that's how the tickets work like. And yeah, this is very useful also for these resources, so you don't have to guess where is your report, where is your drawing, where is etc. Because everything is stored and organized through the centralized data. So yeah, to summarize, on this webinar, we have too many common safety and operational challenges, and EN 13001 itself prescribes complex procedures and time-consuming steps. But adhering to this standard is key to remaining lifetime estimation and further extension, because that's the standard, the most advanced on the heavy lifting industry. Yeah, non-usage of FAA brings to high risk in structural verification. Some of them I showed you before. So it's really, really crucial to make sure that you're following right and correct steps which do not pose any risk to your further operation. Quick solutions without calculations are dangerous, obviously, but SDC Verifier solution provides all necessary tools with our automatic workflow. So basically all those procedures, time-consuming procedures from EN, they are summarized in our automated workflow. What's also cool is that this is fully automated, and that allows you for changes, so you don't have to repeat the same time, and it saves you over 50% of total engineering time based on our experience. Structural lifetime extension is possible with SDC SAM because it's kind of a centralized data for smart decision making. It collects all necessary data, inspection results, allowing you to reliably use that information for your maintenance and other structure. And what's also good is that the maintenance workload can be planned because you assign these tickets to people. You see where it came from. It's not a black box. It's synchronized. So you are definitely make sure that these organized jobs are made on time with a clear timeline. That's briefly it from my end. Unfortunately, we had only 1 hour. We still have a couple of minutes left, and I really hope that it was clear for you. So if you have any questions, please do unmute yourself, ask them, or drop them in the chat. I'm going to check quickly if we have any. But I think unmuting yourself and asking them is the best idea. Okay. I don't see many questions, so I really hope that it was informative and clear. Otherwise, yeah, if you notice something unclear, or if you are interested in something, you can of course contact us separately, or me myself, or at support@sdcverifier.com, and we will be more than happy to arrange a separate call with you to discuss them. Hey, Eric, I see you want to speak. I just allowed, but I'm not sure if you got a permission. Can you confirm? Okay, probably I was too late. Eric, you're here? I saw the raised hand, but I'm not sure if I was on time to accept. Okay, I see something went wrong, probably because I see you joined and then left. Eric, you still here? I really hope that it's not a technical issue from my end, because I did accept. Yes, still here. Okay. Okay, please do use the chat. By the way, good to see you again. Okay, well, Eric is writing a message. Any more questions from anybody here? Is the software running on SDC server or your own company server? That's a good question, and yeah, we're thinking about it, and we came to conclusion that it's always better to run it on the company server, also for protection data. So basically, there are options. It can be run on our server, but if company prefers to run it on its own server, this is possible. Okay, I hope that this answered your question. Do we have more? Okay. Yeah, anyways, you're free to contact me or us at any time convenient for you. I really like you joined today, so thank you for your attention, and hope to see you next time. Thanks again, and best of luck.